Okay, so let's go ahead and get started. So I got a lot of announcements today. And so homework 6 is due today. You know that. Homework 7 is going to be online soon. That'll be your last homework before your midterm. So your midterm exam is coming up next week, so you know that on the syllabus. And so I'll say a few things about that today. I might wait till everyone gets here. Maybe this is everyone, but we shall see. There are other exams going on, or? Okay, yeah. Oh, there's a 1:30 exam today? Oh, okay. Well, lots of exams, it sounds like. All right. And so here's the news that you probably all will like a lot. And I apologize, but I'm going to have to tell this news while I calibrate my screen. But basically, your lab number 2 that you're working on right now, it's not due next week. We're going to make it due after spring break. And so that will give you enough time to do a good job writing up this lab. Unless you had some other plans for spring break, but you guys are EE, so probably not. Yeah, that's all lab sections. So if you're in the Monday lab section, you will still be staggered versus you're still the last lab section. So the Monday lab section lab is actually going to be due the week after spring break on the Monday. The week after spring break on Monday, okay? And everyone else's lab is due at your lab session on spring break, and that basically you'll get your lab number 3 at that time too. So, in fact, you may get your lab number 3 sometime next week. I might just pass it out sometime next week, and you'll have plenty of time to do that. We basically do this every semester. We give you the fake deadline, which would have been next week, and then we give you the extra week because we know that if we do that, you'll be working at least decently towards it, and then during spring break, you can enjoy yourself if you're not really an EE. Right? You can go somewhere, whatever you want to do. All right, so more announcements here. I'm going to miss lecture this Thursday like I announced before. I have a solution for this, though. I have figured out how to record off my computer by itself without the need for any of this stuff here. Except that I need to have a microphone to do that. And so I have a microphone, but it's not something I can attach to myself. It's something that sits on a desk. So we're going to go do the lecture on Thursday. On Friday at 3 p.m. I don't know if you can make that. If you can, try to come. But if you cannot, this is going to be recorded anyway. And actually, the quality of the recording is probably better than what occurs in this room right here. Both the video and the audio is probably better. Oh, discussions at 4. Yeah, that's interesting. I might be able to change this time one more time then, so we'll see. If I do that, then I'll send an email around. Is there anyone here who does not receive the emails going to that EE140 Google thing? This is not representative of the whole class, so hopefully people will know. What's that? Well, what I'm saying, it won't be webcast, except I found software that I can put on my computer that will automatically record. Well, I'm going to send it to the webcast people, and they'll put it on the webcast website. Okay, so I guess that's all the pre-lecture materials for this lecture. They're online already, so you can get those. I'm not going to spend a lot of time on them, but before even doing the lecture, let me talk about the midterm exam. So I guess enough of you are here that I'm going to pass this out now. This is information about the midterm, so let's just pass this around and go through it. And these are an old exam. This was spring 2009, the other time that I taught this particular course, so I figure I'll send this around for you. Say a few more things about that too, because there's obviously other faculty who teach this course. And you can grab those exams too. I think you can get some off of the ADCAP Anu website and that sort. But I'll just warn you, those exams may not be similar to the types that I give. And so this that's passing around is probably most representative of the type of exam that you will probably get next Thursday. Let's see, let me... Okay, so let's just take a look at the info for the midterm here. So this is passing around. You'll have this as a sheet. This is also up on the web as well. But to support the midterm exam, I'm going to have extra office hours next week. I'm going to miss my office hours this coming Thursday because of this meeting that's making me miss lecture. So there won't be office hours on Thursday. But I will have my regular office hours on Monday. All the TAs will have their regular office hours, and I will also have an additional 2 hours of office hours from 10 a.m. to 12 noon on Wednesday, the day before the exam, which I find to be the most useful time to have such office hours in case you have questions. So please come by, ask questions on anything at that time. The date of the exam, same as your syllabus. This is going to be March 17th, 12:30 to 2 in this room. So it's going to be just like a lecture, except get here as early as you can because I want to maximize the amount of time that you have taking this exam. We have a class before this class. We have a class after this class. So I won't be able to give you any extra time to take this exam. So you need to be able to work fast, which means you probably want your inspection equations memorized or have some kind of comfort with them so that you don't have to look at a sheet to find them. Now, that said, you can have a sheet. Okay, so the exam is going to be closed book, except you'll be allowed one sheet on which you can write anything you like. Yeah, double-sided. Anything you can fit on that 8.5 by 11. Anything you can fit on that 8.5 by 11 sheet of paper, that's fair game. Okay, put all your inspection formulas on that, put everything on that. People have even taken lecture notes and shrunk them down to tiny sizes. And then have a magnifying glass if they need to look at it. I don't care how much stuff you stuff on this. You can do whatever you want with this single sheet, okay? But my recommendation is don't make it such that you're going to rely entirely on this little sheet because you're going to run out of time fast. If you are second-guessing yourself too much and you're saying, oh, I think I know that inspection formula, but let me check anyway, right? You're probably going to waste too much time. And in this kind of exam, right, you've sort of seen it in your homeworks and everything. It's important to be able to do things fast enough, okay? Let's see. You'll be provided with exam sheets, enough space to put all your work on these sheets. Show and include all your work on the exam sheet. You can't just jot down an answer unless it's an inspection thing. If it's inspection, we'll let you jot down the answer. Okay, but for any other thing that requires some kind of derivation, you need to show your work, how that was derived, how you arrived at the formula. And as I've said before, right, there'll be calculation on this exam, okay, because I care about numbers. And I want to make sure you know order of magnitude numbers because knowing order of magnitude numbers is arguably more important than knowing the equations themselves, especially when you're doing research, right? When you want to decide whether you're going to go in one direction or not, you got to think numbers. You can't just think equations. All right, so we want the equations, but we also want the numbers from you. And my advice is if you're solving a problem, don't plug the numbers in till the very end. Get a closed form solution to the problem, then plug the numbers in. Okay? The way these are graded, most of the points are coming from the solution, the expressions that you derive. So if it's a 15-point problem, maybe 3 or 4 of the points come from calculating. Okay? More likely 3 or something like that. All right? So it's more important to get the expression, then at the end do your calculations. It's also better for you too, because you need to have the art of looking at that final expression and saying, does that make sense? Are the units of that thing correct? Because if they're not, then you probably got it wrong and you probably made some error somewhere along the way. Okay? During the exam, make appropriate engineering decisions and approximations in order to simplify your analyses so that you can do the problems quickly and with fewer errors. In other words, you can use inspection analysis when you want, and you can neglect things if you think they can be neglected as long as you're within 10% of the correct answer. All right? Now, getting within 10% by luck doesn't work, right? If you have the wrong expression and you have a number that's within 10% by luck, no, you'll still get it wrong. If you have the right expression and you're within 10%, it's okay. All right? What's the material to be covered? Darn. That should be reading in Gray. Gray and Meyer instead of Razavi. I sort of copied this from last year. So Razavi was the text we used to use. Okay, so correct that right now in your thing. I'll put a corrected version up on the web there. But class lecture notes, handouts, homeworks. Exam includes all material covered so far in class. You may pay more attention to the following areas. And this is just a summary of areas that come to my mind immediately, which means there's a high probability that something on these areas will be on the exam. So bipolar, MOS, small signal generation and analysis. Single and multiple transistor amplifier circuits, both BJT and MOS, including cascades, either actively or passively loaded. You should be able to determine bias points, gain, impedance, frequency response, all the things we've been playing around with the whole semester. Differential pair amplifiers, so either actively or passively loaded, including concepts like biasing, differential common mode gain, CMRR, half circuits, various impedances. We've already discussed all of those things, and we'll discuss even more today. Input offset voltages, which we'll discuss today, actually, and you'll have on your homework this time around. Transistor bias generators and current sources, including the ability to determine output current, output resistance, output swing for a circuit in a possibly unfamiliar current source. So you've had current source type stuff in homeworks and in lecture. Should be able to design the current source, so choose the W over L ratios that give you a certain swing, for example. And then finally, well, not finally, but biasing and small signal analysis of single and two-stage op-amps. We'll hit two-stage op-amps by this Thursday. And so the coverage of this exam is everything up to a week before the exam, which is this Thursday, which is really this Friday. Because we're not having the Thursday lecture, we're having that Friday at 3. Possibly a little earlier so you can have your discussion section too. Analysis and evaluation of circuits using op-amps with finite gain, finite bandwidth, and or input offset voltages, which we'll talk about today. Okay, so that's coverage of this exam. I'm talking about this earlier than usual. Usually I would pass out this exam material on Thursday of this week, 1 week before the exam. I'm just a little early this time because there's no lecture on Thursday. Okay, now in addition to this exam, you have this solutions to my midterm. How do I go about maximizing this window if I can't access the top thing? All right, forget it. You have solutions like this in front of you. You should go through, take a look at the solutions. When you do this, I wouldn't look at the solutions immediately because, of course, problems look a lot easier when you look at the solutions, right? So if I were you, I'd cover up the solutions and try to solve these problems by yourself without the solutions first, because I'm telling you, these solutions make it look very easy, but it wasn't necessarily easy. You can see the average was a 66, which in my opinion is not bad. That's okay for an average. It's about where it should be for a class like this. And how consistent is that? It's probably consistent or so. So when you're taking this exam on Thursday, probably you can expect a similar type of average. Yes? What's that? No, those are points, actually. Yeah, so what's the total number of points on this exam? I think it was 100, but you can add it up. Is 115? Okay. Yeah, so it's right around 63 or something is the real percentage average. Yes? Yeah. Yeah, that's right. And so I forgot to pass out one of your homeworks last time. I think some people came up and picked it up, so I should pass these out too. They aren't? Okay. All right. Which ones are missing? They should be. The 5 and 6 are not posted? Yeah, 4 should be posted, but 5 and 6, yeah, okay. I'll make sure those get posted immediately, I suppose. And, you know, the grader's going through your homeworks as well. So we'll try to get all this done at least by Tuesday next week. No, but the posting by probably Thursday this week. Okay? Yes? Yeah. This was exactly the same situation. There's a class before, a class after, so you waste some of that time. Okay. How do I get rid of that? I think I have to get rid of it this way. All right, so let's go into lecture material here. We went through all of this. So I went through midterm exam info. We're going to talk about offset voltage and finite gain bandwidth product this time. But first, let me finish up with business from last time. So last time we were going through this op-amp sheet here. I think I have to be at 125 here. Let's fix this. So these lecture notes that were handed out, we've pretty much gone through the whole thing. And we made it to the very end here, where the last thing we did was analyze this current mirror loaded differential pair in MOS. It's a similar type of analysis for the bipolar version of it. The neat thing about this was the output resistance of this thing was determined by a current mirror effect. So there was actually feedback here. So to determine this output resistance, you would drive this output here. Some current would go into the R0 of M4. Some current will go downwards into this resistance, which is a 2R0. But then that current spins back, goes into this current mirror, and comes back up here. And so you end up seeing effectively 1R0 looking downward too. So you get a parallel combination of R02 and R04 as your final resistance there, impedance at this point. So your gain then becomes GM times R02 parallel R04. Okay, we went through that last time. There was lots of questions. I guess I'm not going to spend too much more time on that. We then did CMRR, common mode rejection ratio. And the last thing we were doing was looking at this, this final factor that's important to us, which is the common mode rejection. Well, the common mode range in this case. So we looked at common mode rejection, but we now wanted to look at common mode range. And so what is common mode range? That means what is the largest input signal and smallest input signal that you can apply to these two inputs. And it's common mode, so you're basically driving both of them with the same voltage. What's the smallest voltage and what's the largest voltage that this amplifier can take? And that's usually going to be a DC bias point. All right? And so in order to determine that, you know, we've done this before with simpler circuits. It all comes down to when does a transistor go out of saturation and into the triode region for the case of MOS. Okay, and you know that transistors go into the triode region when? When their VDS voltage is less than the over voltage that you're expecting. Okay? So if I were trying to look for the lowest common mode signal that I can apply at the input here, I would have to look at these transistors M5 and M1 here. Okay, so first of all, I can't turn M1 off, right? And I can't drive M5 into the triode region, which means that the lowest common mode signal that I can apply to the input has to be one that still allows a VOV across this M5, and that still allows a VGS across M1. Okay, and therefore it's easy for me just to write down this common mode, the smallest signal that I can apply to the input. That's going to be VSS, which is the lower rail voltage, the negative rail voltage, plus the overdrive voltage of device 5, plus the VGS of device 1 or device 2. Okay? And if I add all of these things together, that's going to give me the minimum voltage that I can apply to this circuit here without turning one of these transistors off or turning one of these transistors to the triode region. They all remain saturated if I apply voltages larger than this to the input. And this is just expansion of that equation there. Okay, so pretty simple how to get this. It becomes a little more difficult looking for the other range. So this, when we're looking for common mode range, right, I've got to first look at the smallest signal I can put into this amplifier, and then the largest common mode signal that I can put into this amplifier. So now we're looking at the other side here. So we've got to go back to this amplifier here, and we have to think to ourselves, what about the high end? What's the largest signal I can put into this? And so what is going to determine what that largest signal is? I actually have a picture of the amplifier there. If I were looking at this, and again, I'm applying a common mode signal to it, so both inputs are getting the exact same input. Not really I'm applying a signal, I'm applying a DC bias here, right? I want to see how high I can pull up my common mode input. Okay, so I can write here that VICM max, which is my maximum common mode input voltage that I can apply right here. So this is where I'm applying that, VICM there. In nomenclature, that's usually given CMR plus for the positive going, the largest signal that you could put into this. So what's that going to be equal to? Well, it's going to be defined first by the voltage, the highest voltage you can get to, which is the supply voltage, VDD, right? So VDD sets the starting point for that. But you're probably not going to be able to raise that input voltage all the way up to VDD, because if you did, you would probably take M3 and cause big problems for M3, right? So when would M3 have a big problem? Yeah, but its overdrive voltage in this case is equal to its gate to source voltage. Or actually not its overdrive, its drain to source voltage can't get lower than the gate to source voltage here, right? So actually, I have to keep this input such that this node always stays below VDD by a gate to source voltage of device 3, okay? And so I'm going to write that by VDD minus VGS of device 3, 4. Okay, where 3 and 4 are the same, so they have the same VGS. I could have just written VGS 3 for that. And I put in absolute values because it's a PMOS device. All right? And then what about this device here? See, what you have to do is get from VDD, which I'm doing. You have to jump here, jump across that device, then jump back here, okay, to get to the input. So the game we're playing here is how do we get to the input from one of the rails. All right? And so I know that from this rail, I got to drop at least VGS across this transistor because it's diode connected. Across this transistor, I've got to drop at least an overdrive voltage, otherwise it'll go out of saturation. Okay? So I can write as another term here that I've got to go down another overdrive voltage, but this time an overdrive voltage VOV12. To keep device 1 in saturation. Okay? And then finally, to make it back to the input, I have to add to that the VGS of 1, 2. I got to go back up in voltage because I've dropped down to this point, but this now makes me go back up in voltage to my input. So now I'm going to add to that VGS of 1, 2. Okay? And that's it. That's what my largest voltage that I can apply to the input is that prevents any transistor from turning off or going out of saturation in the triode. All right? And I can now expand these things. So expanding all of those things, this ends up being VDD minus ISS, which is 2 times the IS of one of these transistors, times mu PC aux, times W over L 3, 4, all under the square root. So you can see that as pretty much an overdrive, minus the threshold voltage of 3, 4. So I'm really just expanding out this VGS 3, 4 thing here. And then plus VT of 1, 2, where the overdrive voltage of 1, 2 canceled with this overdrive voltage term right here. Okay, so in the end, this is what my VICM max voltage becomes. And again, it's all procedure. You know how to do this by procedure. You're going to get some practice doing this on this upcoming homework here. But when you see that part of the assignment, just do this. Start at one of the rails, go through each transistor until you get to the input, and make sure each transistor is going to be on or saturated. And you'll see that we did exactly the same thing going down here. From the bottom, we went from VSS through that transistor, through VGS to get that previous result on this page right here. Okay? Any questions about doing this? Yeah, I guess I should be clear. Yeah, that's ISS there. Do I have that anywhere here? I guess I don't. So, yeah. I used it even here. I should show that as ISS. Okay, so that's it for op-amps. Let's move on to another topic now, which is offset voltage. And with that, I'm also going to use some prepared notes for that, but then I'll stop with this and I will actually use some, quote, real notes or written notes for this. Whoops. We'll get there eventually. Okay. All right. So input offset voltage is another non-ideal op-amp phenomenon that you have to worry about in general. And this is actually something that you'll actually see more often than not when you're hooking up certain types of circuits. And so what is input offset voltage? It's a voltage, it's a fictitious voltage that we make up to model the effect of mismatches in your op-amps. Okay, so in our differential pairs, well, we've been discussing these things all the way up to now, basically assuming that everything is matched, right? So we have a purely symmetric circuit. This resistor on one side is the same as this resistor on the other side, and the transistors are also matched up completely. So what happens when that assumption breaks down? Okay, so in actual circuits, you get these device mismatches. And what happens is because R1 doesn't equal R2, and M1 doesn't equal M2, and M3 doesn't equal M4 exactly, there's always going to be little variations between them, statistical variations. You'll get an output when your input is 0. So like in this case here, if I ground out both inputs of the op-amp, I don't necessarily get V0 equals 0. If everything were ideal and everything were matched up, V0 would be equal to 0. But in reality, because of mismatching within this circuit here, V0 does not equal 0. And that's even with V plus equal to V minus equal to 0 there. Okay? And so that's a problem, but there's an additional problem here is that sometimes the base currents of the transistors, if you have a base current, the input current of the transistor, if you have an input current, sometimes they're not equal either because the transistors are different. So in a bipolar circuit, if you have Q1 and Q2 in your diff pair, right, they may have different base currents. And if they have different base currents, that's now an offset current. And that can also cause an effect where your output is not 0 when you're applying a 0 input to this thing. Okay, so both of these effects we have to model. And the way that we model them is through this circuit right here. Okay, so what I'm drawing here is an op-amp symbol, obviously. But within this dotted box, this dashed line box, I'm saying this is an ideal op-amp now. Okay, the actual op-amp was this up here. Okay, it had all sorts of problems with it because when I put 0 input voltage, I have a finite output voltage that's not 0. Okay, this op-amp in this box now is an op-amp where if I did put 0 volts on it, its output would be 0. Right? This is an ideal op-amp. But now I want to model this actual op-amp by adding a couple of sources to this. Okay? So if I add a VOS to the input, and I add an IOS also to the input to model an offset voltage and effective offset current, then those two additions that I give this circuit can model exactly what this op-amp is doing. Does that make sense? Okay? So now I can keep analyzing using an ideal op-amp, except I have these additional elements here that tell me what the real op-amp does. Okay? And so, of course, this VOS is called an input offset voltage. The typical value may be 1 to 5 millivolts for bipolar transistors. It used to be worse for MOS, and maybe it's getting worse again because we have such small transistors again. But for MOS, you can expect values like this, maybe a little bit larger sometimes. Input offset currents, 0 for MOS, right? Because MOS has an infinite gate impedance. And so there's no current for MOS, but for bipolar, you have to worry about it, and typical values on the order of 10 nanoamps. Okay, so you might ask the question, why do these things matter? Okay, they're so small. 10 nanoamps is a pretty small current. 1 millivolt, 5 millivolts, that's not that large. That could be significant, but that's not that large. So why are we so concerned about these tiny voltages here? Well, here is an example here where this can really affect you. And so this is an integrator, right? Something that you've played around with before. And I think in a course like 40, you've hooked up integrators like this. So here's your op amp here. You just put a capacitor from the negative terminal to the output terminal, and you have an input resistor coming into this, right? And so you've usually played around with this as your integrator in your previous courses. But in actuality, if you tried to hook this integrator up on a board, it would never work. Okay? And the reason why it would never work is because no op amp is perfect. Every op amp has an offset voltage there. Okay? And so if the real op amp has an offset voltage, which I am modeling with this VOS voltage right here, then what happens in this situation? Then, because of the op amp, the ideal op amp laws, right? This op amp is now ideal. The non-ideality is represented by this VOS here. But because of the op amp and its high gain, you know that the plus terminal equals the minus terminal. The voltage on the plus terminal equals that on the minus terminal. So that means on the minus terminal, you have a VOS voltage there. Okay? That could be 1 millivolt. It could be 5 millivolts, somewhere in that range. It's a very small voltage, but it exists. Okay? And if I have a VOS on that minus terminal, what's going to happen here? That VOS is dropped across this resistor. If I have a voltage across a resistor, that's going to draw a current. No ifs, ands, or buts about it, right? That's the law. You're going to get a current through that resistor. If I get a current through that resistor, of course, it's not going to go from the negative terminal of this op amp if it's an ideal op amp, right? Because the negative terminal has an infinite impedance. The way it's going to go is you're going to draw that current from this capacitor. Okay? So you're basically sucking charge away from that capacitor, creating a negative voltage on this side, a positive voltage on the other side. Right? Well, that positive voltage on the other side, it never stops, right? It just continues to rise because this voltage isn't going away here. Right? That voltage is the offset voltage. It's just sitting there. And that's just going to keep sucking current out of this capacitor here until this voltage here, you know, if I had an infinite rail for the output, that would go to infinity. But what will really happen is it's going to go up here until it hits the voltage rail, and then it flattens out. So you can try this in the lab. Just take any op amp, because any op amp is going to have an offset voltage. Hook up this integrator here, and you'll see there's no way this can work because this output is going to go to one of the rails. It's either going to go to the positive rail, as is the case in this right here, or it's going to go to the negative rail if I had an offset voltage that was in the other direction here. Right? So you can never bias up this op amp if you just stuck a resistor here and a capacitor across here, and that's all because of this offset voltage. It's all because it is an integrator, and the offset voltage gives it a constant input, so it constantly integrates that input, and the output voltage rails out. Okay? How do you fix this problem? And the only way you can practically get an integrator to work on a breadboard or on your circuit or so is to put a dummy resistor across that capacitor. Okay? If you put a resistor across that capacitor, and it should be a huge resistor, so that it doesn't interfere with the impedance of the capacitor, right? You want the capacitor impedance, which is 1 over SC, to be a lot smaller than the impedance of this resistor. But if you put that resistor across here, that's going to force a negative feedback loop that's going to keep this output voltage grounded at very low frequency, at DC. Okay? Does everyone understand what I just did right here? How the offset voltage was hurting us here? Yes? Yeah, you can try to do that, but, you know, how accurately are you going to match this offset voltage right here? So, right, say this is 1 millivolt. Say it's 1.005 millivolts, right? And so you're putting a voltage right there, and you're spinning it trying to get to 1.005, and then you get 1.005, and it's gone. But then noise changes this to something else, right? So it's just difficult to track there. The best solution is this huge resistor out here. You're not sacrificing anything by putting this huge resistor out here, except if you're on chip. Because if you're on chip, that resistor is going to be enormous. So on chip, there are other solutions to creating circuits like this that we'll talk about later on. But right now, I just want to focus on this this offset voltage could be very problematic here. Okay? Yes? This resistor helps because it closes a negative feedback loop. Right? So what's happening here is that once this resistor hits, it creates a gain across this, right? That's finite now. Right? The current no longer goes into this capacitor. The reason why this voltage keeps rising and integrating is because the current goes into the capacitor. Right? With this resistor here at DC, or we're talking about the DC value. At DC, this capacitor has an infinite impedance, right? This resistor here at DC is going to have a smaller impedance than that capacitor, so the current will choose to go through the resistor instead, right? And that will bound this, right? This now becomes a non-inverting amplifier. Right, where the gain of that non-inverting amplifier is going to be whatever you choose between these two resistors right here. Okay, so you have a bounded problem now with resistors. With the capacitor, it's not bounded. Right, the capacitor just keeps charging up. Does that make sense? Okay. So now that we've talked about this offset voltage and how bad it is, let's talk about how to determine it for our actual circuits here. All right, so what I want to do is sort of take an example trying not to do it the easy way. So I got to find the notes on this. See, the easy way would be this way, where I would just bring this up and go to the next page. Now, if you want, I could do it this way, but I'd probably be going too fast that way. All right, so I won't do it that way. All right, so what I want to do is get the offset voltage of a source-coupled pair for you and just derive this. So what I want is the VOS of a mismatched source-coupled pair and the objective of this exercise is really to derive an expression for VOS. And so for this, I'll draw a little source-coupled pair here. Actually, let's see if I can cheat. No, I can't. Okay, so there's your source-coupled pair where I have an M1 and an M2, but now these are not equivalent devices. They differ by a very, very small amount. Okay, instead of calling these both RDs, I'll call them RD1 and RD2, where these also are no longer absolutely equivalent. I have my current source, my bottom voltage rail, and then I'm still treating this as a differential amplifier here. So I'm interested in this voltage here, VID between those two inputs. And in order to find the offset voltage for this thing, what I need to do is equate this, again, to what I just did with those op amps there. equate this to the same thing. So I guess I'll redraw this thing here. Except the same thing, an ideal version of the same thing. So here's all of this again, where I have an RD1, RD2, but this time these are equal. I should say these two are not equal. Okay, then I have an M1 and an M2. This time these are equal. And then I have my inputs right there. And so what I want to do is sort of put this in a box and say, okay, this is the ideal version of this differential pair. So this is ideal source coupled pair with a matched devices, M1 equal to M2, and RD1 equal to RD2. Okay, so everything in that box is ideal. I'm assuming everything is matched and balanced like we've been assuming throughout all of these lectures so far. But now what I'm going to do is equate this to the circuit on the left, which is not ideal. Okay, so this is an actual source coupled pair. With mismatched transistors and resistors. Okay, I want to equate these two, but in order to equate these two, I have to attach this to it, which is my offset voltage, VOS. And what I want to know is what has to be the value of that VOS so that the circuit on the right completely models the circuit on the left. Okay? So how do I go about doing that? I have to first consider what things contribute to mismatching of this circuit. Okay, so I get my VOS. And that VOS enters or arises due to variations in the following things. So one, the transistors themselves. So transistors M1 and M2. Okay, so what can vary in these transistors? Well, anything can vary in these transistors, but usually you're going to focus on their W over L's because those are determined by lithography, and lithography can vary across the wafer. And even their VTs can vary. And I'm not talking about variations in VTs because of body effect and that sort of thing. I'm talking more variations just because of process or technology differences between them. Okay? The other thing, of course, that can vary in this circuit that we have to pay attention to is the fact that these resistors, RD1 is not equal to RD2. And if these are different, of course, the immediate thing you can see them doing is causing variations in the gain of the circuit. Okay? So I want to model those variations there. And I want to include these variations in W over L, in threshold voltage, in resistor values. I want to include those in my expression for VOS. Okay? So with that in mind, let's now write down our definition for VOS, which we just looked at in the case of op-amps here, but it's the same thing in this case. VOS is equal to the input differential voltage needed to get the output differential voltage, VOD, equal to 0 volts. Okay? In the following circuit. Okay? So here's M1. here's M2. And so what I'm doing is zeroing out the inputs of this, but I'm including in this VOS voltage. So here's VOS. And I'm just going to attach all of these together there. Okay? So remember, this is how we're defining this VOS voltage here. So I can pull this back up here. Right? VOS is defined as the voltage that when you hook this op-amp up like this, you ground both its inputs, that voltage makes the output equal to 0. So I am simulating that exactly in my derivation here. Right? This is exactly that. I'm putting both inputs to my op-amp in this case, this differential pair. I'm grounding everything out, but VOS is in that loop because I want to find the value of VOS that makes my output equal to 0. Okay? And so whenever you have something like this, the natural thing to do is just start solving this circuit. So I know that I'm dropping a VGS across M1. I know that I'm dropping another VGS, VGS2 across M2. And I'm being very specific about which VGSs because they could be different because these transistors now are no longer absolutely equal. There's some difference between them. Okay, and so if I have a circuit like this, yes?
You said that if you model it, then you can assume that the transistors are
No, but once I find out this VOS, then I can assume the transistors are matched. Okay, but until then I can't, right? Because I want to find out what that VOS has to be that once applied, then I can assume they're matched, okay? So right now I'm going to assume they're not. So I'm going to use KVL, Kirchhoff's voltage law, around this loop here, and I'm going to be able to write that VOS minus VGS1 plus VGS2, that has to be equal to 0 in the end, right? And so in a way I am modeling this as ideal in this case, right? But I have to take into account the differences in the transistors, which you'll see me do in just a second here, right? The currents will be different, etc., because they'll vary a bit. And so this has to be equal to 0, because if this is equal to 0, right, then the output's going to be 0 for this, okay? And so therefore I can write that my offset voltage is just going to be VGS1 minus VGS2, which I can continue to expand and write as VT1. So here's where I'm taking into account the differences in these transistors, right? So VT1 plus an overvoltage, so that's 2ID1 over mu n Cox times W over L1, all under the square root. Okay, minus the VGS2, which is going to be minus a VT of 2, minus an overvoltage of device 2, which I can write as a similar equation, but with the ID and W over L of device 2. Okay, so that now becomes my expression for my offset voltage. And just rearranging this one more time to get all the VTs on one side. So this now becomes VT1 minus VT2 plus this again, 2 times ID1 mu n Cox W over L1 minus this other term, 2ID2 over mu n Cox times W over L over 2. Okay? So let me call this equation 1 as part of my derivation because I'll refer to it again. And so in order to get VOS in terms of things we understand, because right, this is a random event, right? When two resistors or two transistors are not equal, how do we know how different they are, right? So say two resistors, R1 and R2. How do we know if R1 is bigger than R2? How do we know they're not equal? How do we know right after we fabricate? We don't know, right? So it's all statistics. And so the way we really want to model this to get a VOS is to express things in terms of percent changes, right? So we've talked about percent changes before. If I have a parameter x, a percent change in that x is like delta x divided by x, right? So I want to express things in terms of a delta x divided by x. In particular, in this case, I want a delta W over L divided by W over L as part of my VOS equation. Okay? Now, we talked about these before when we talked about current sources and matching of current sources. So I'm not going to spend the time rewriting a lot of that nomenclature. I'm just going to steal it here from things I've already written here. Okay, so let me just grab this, pull it over to here. And so we can define difference in average quantities. All right? So ID equals ID1 minus or delta ID is ID1 minus ID2. ID is equal to the average of ID1 and ID2. Remember this? We did this for current sources before. Okay, exact same nomenclature here, except now I'm doing it for the IDs, the W over Ls, the VTs, and the RDs. Because those are all parameters that can change, and because they change can give rise to this offset voltage VOS. Okay? And so, continuing to cheat, because you don't want me to go through all this stuff, believe me. You will be asleep in just seconds. Okay? But continuing to cheat, right, I can take all of these equations that I had before, rearrange them to solve for just the actual parameters themselves. So remember, just like the current source thing, ID1 equals ID plus delta ID over 2, so on and so forth. ID2, ID minus delta ID over 2, so on and so forth for all of these different parameters. And now what I'm going to do is take these parameters that I've expressed in terms of a delta term and an average term and plug them into this equation number 1 here, right? Here's ID1. I'm going to plug into ID1 this ID plus delta ID over 2. So everything that's up here, I'm plugging into that original equation, right? It's going to create for me a pretty hairy set of equations here, but all the math is here. I don't want to go through and do it because, again, the sleep factor would be high there, right? But if you go through, and you can look at this after lecture, if you go through and do all of this, so there's even some mathematical tricks here. You have to apply the binomial theorem, where you actually make an approximation, right? 1 plus n times x to the m power is 1 plus m times n times x, as long as x is very small. Do you remember that? Okay. And so if you apply that binomial theorem, you make some cancellations in this equation. Everything boils down to this equation here, where VOS is equal to the delta VTs. So directly, the difference in the threshold voltages of this thing, plus 1/2 VGS minus VT times the difference between delta ID and delta W over L. Okay? Now, I might want to express this instead of these delta IDs, right? Because delta ID is not one of those things that I can control through technology, right? What I can control through technology is W over L's, the resistor values, etc., right? So I can convert this delta ID into resistors by just understanding the relationship between the currents and the resistances. And to do that, more theft from the other side occurs. Right? And so when VID equals VOS, then VOD equals 0 in this circuit. In this circuit here. Okay? So the output differential voltage, which I guess I should write here. That output voltage equals 0 when VID equals VOS, okay? And at that point, then I can say that ID1 times RD1 equals ID2 times RD2. And so the mismatch in ID is basically caused by the mismatch in RD, right? And so I can write this equation, delta ID over ID is equal to minus delta RD over RD. And so finally I can express this offset voltage equation in terms of exactly what I want. The difference in threshold voltages between the two input transistors, the percent change in the resistors, the percent difference in the values of the resistors, and the percent change in the values of the W over L's of the transistors. These are all things that have to do with the fabrication process for this device. So this thing right here That, of course, is our threshold mismatch. That's something that you can control by your threshold implants. Well, you can't really control it, but you can try to minimize that variance across the wafer by using a threshold implant that's maybe more controllable. These things here are basically geometric variations. Okay, so for example, they're caused by fabrication tolerances, maybe by lithography, limitations. But they can be controlled by layout, right? So if you have lithography that can't make two lines exactly the same, so for example, you're trying to make that line, you make this line, and that distance is not quite equal to that distance, right? So how can you make them a little more equal on a percentage basis? You can make those lines bigger, right? So if I made this line like that and that line like this, then these probably still will be mismatched, the total width of these lines, but the percent mismatch will probably be less, okay, in a fabrication process. So just by making things bigger, you can reduce these offset voltages. Of course, that's not really an option all the time because, as you can see, integrated circuits, you keep wanting to make them smaller and smaller. So as we get to the very small sizes, we're always pushing the edge of what we can do with offset voltages. So yet another thing analog designers have to worry about as digital takes over is the fact that these gate lengths are getting so small they don't have as good control over them, right? Unless the technology, the equipment keeps up with the size of them, and it generally does, right? So even though the equipment's getting better, you're making things smaller, so your offset voltages aren't getting any better. They, in fact, may be getting worse in a lot of these processes out there. Okay, and so, it's the same kind of thing with current sources here. These negative signs right here, pay no attention to these. Okay, because they can easily, delta RD can easily be negative. Delta RD over RD negative, and delta W over L over W over L could be negative too. This can easily be the case. So anytime you work with these types of equations where you're looking at the offset voltage as a function of delta, a percent change in something, you always take the worst case. So no matter what the sign is, you add everything. Okay, because that will be the worst case in this. Some interesting things that I could say about this here is that these geometric variations here, they pretty much scale with the overdrive. You notice just from that term there, they scale with overdrive. So one way to alleviate this problem, right, if you're trying to get to the smallest sizes possible, and you're just not going to be able to control this geometry, is to try to make that overdrive voltage as small as possible. Okay, that's consistent with trying to make supply voltages as small as possible as well. So these things at least come hand in hand. This threshold mismatch thing, it's more difficult to control here. Okay, and so threshold voltage is something that, as you get to smaller sizes, can you control this well enough to get good analog circuits? So this is just another instance where analog designers struggle more when things get smaller and smaller. Now, I just did a very detailed exposition of offset voltages in MOS, and all of this derivation is actually in this handout that you have online as well. So every detail of it. But beyond this, there's a discussion of offset voltage in bipolar case. Okay, so this is the emitter-coupled pair here, the mismatch emitter-coupled pair. I'm not going to say anything about this. I'm just going to say the analysis is exactly the same. The equations are a bit different, but you can see this same analysis being done around the loop of the input devices, trying to find that offset voltage. Equations end up looking a bit different, but you still end up with an offset voltage equation that depends on sizes of resistors, on currents in here, which you can convert. Actually, this is saturation current, so that's a property of the device. Okay, so it's mismatches between devices and resistors again that you can derive this. And I'll let you go through this yourself and look at the bipolar case. It's really the same as the MOS case. This also talks about input offset current for an emitter coupled pair. I'm also going to let you look at this by yourself because these days it's more MOS that's become more important. Bipolar is still important when you're using, say, off-chip op-amps or so. But if you're doing completely on-chip design, most of that is MOS these days. And this current mirror thing, so you can also derive offset voltages for current mirrors as well. In this case, instead of having a term out here that depends on a delta R over R, you instead have a term that's delta W over L for the active load devices. Okay, so you still end up with mismatch between load devices, and they now dictate what the offset voltage is. But all of this stuff, I'm just going to let you read through it yourself, because I've gone through most of the essentials. This is just like more reading material for you. Okay? Any questions about offset voltages at this time? Because I'm about to leave this topic and go to a finite gain bandwidth topic. Okay? You'll get a little bit of practice dealing with this in your upcoming homework. All right, so now let's talk about another topic that you know a little bit about already, and that we've actually talked about to some extent already. And because of that, I am going to cheat again. Well, let's not cheat just yet. Let's slow down on our cheating and do one thing before this. So the next topic is finite gain bandwidth. And I will cheat a little bit by grabbing this thing. And so we had already discussed this thing here, so there's no real need to go into great detail about this. Okay, we went through and got the gain of this thing. But one thing we did not do at the end of before the previous lecture is get the bandwidth of this thing. Okay, which you've already done this now on your homework. Okay, which is good because it's good for you to explore how this kind of stuff is done here. So you can just tell me what's the frequency response of this thing. So if I wanted to get frequency response, can you just do that by inspection for me? So one thing I'll say is that usually in this type of, if you're using this as an op-amp, it's usually going to be an on-chip op-amp. And you're going to have some capacitance at this node right here that's coming from the next stage. So that capacitance is capacitance from next stage. In addition to that capacitance, you're going to have all of the capacitors due to these devices. So plus those from M2 and M4. So say I call that all CL there as my load capacitance there. Then I can write my frequency response very simply because I know that this node is my highest output resistance, is my highest resistance node, right? And I know I'm going to have a capacitor here as well. It depends on what the source resistance is for the source that's driving this. But in many cases, I can neglect that capacitor and just say this dominates the performance right here. And so I can write the pole frequency down as R0 of 2 parallel R0 of 4 times that load capacitor and 1 over all that stuff here. That's going to be the dominant pole. What's that? RF. What did you say? RF? RO5. Where's 5? Oh, this one down here? No, because it's a differential. So if it's operated differential, then the 5 goes away, and I'm really just using a half circuit to get this. Okay? So the frequency response of this thing, omega h, is 1 over R naught 2 parallel R naught 4. Right? That's the dominant pole of this thing. But what do I mean when I say dominant pole of this thing? Well, I mean something like and here's where I'm going to steal. I mean something like that, right? And so when I'm looking at that particular op-amp, this is that dominant pole, right? So for that particular op-amp that I looked at, this gain right here, we determined last time, was GM times R naught 2, R naught 4, right? And now we know that this dominant pole here is equal to 1 over the R naught 2 parallel R naught 4 times that CL capacitor. Okay, and this then is what its transfer function looks like, and now you can sort of see that this is really beginning to look like an op-amp, but a non-ideal op-amp, right? Because for an ideal op-amp, this gain would be infinity. In reality, the gain is given by this transfer function, which models this Bode plot. Okay? So your Bode plot stuff, right, this Bode plot becomes exactly this, where I just take the gain of this circuit, A naught here, at DC. So if I plug in 0 for S, right, all that becomes 1 at the bottom. The gain becomes A naught. And so on a Bode plot, that's 20 log A naught. Okay? And I just calculated my dominant pole, so I know that I have a response that goes out to my dominant pole, and then from there on goes 20 dB per decade. Down to what I can call a unity gain, right? So the gain here is 20 log A naught, but after I pass that dominant pole frequency, the gain starts dropping, as you're seeing here, until it crosses the x-axis, where the gain is equal to 1. That's 0 dB. Okay? And so where it crosses that axis, where the gain is equal to 1, we usually give that a symbol, omega t. Okay, and omega t is the unity gain frequency. And exactly what I said. That's the frequency at which the gain is equal to 1, or is equal to 0 dB. Now, there's a couple interesting things you can derive just off of this curve right here, things that you should recognize. And one of those is that at the unity gain frequency, you can write this expression, right? Because I know what the transfer function is right here at the top. And so if I evaluate that transfer function at the unity gain frequency, I know that has to be equal to 1. And so that equals A naught over square root 1 plus omega t divided by omega b squared. If omega t is much greater than omega b, which is the case here, right? Because in actuality, this is normally plotted as log frequency, right? So if that's log frequency, then the distance between omega b and omega t is enormous, right? There's several orders of magnitude across there. So omega t is much larger than omega b. That means I can neglect that 1, and everything boils down to omega t is equal to A naught times omega b. Okay? A naught is the gain, the DC gain of this circuit. Omega b is the bandwidth of the circuit, the 3 dB bandwidth. And so this is called the gain bandwidth product. Okay? And every op-amp has a gain bandwidth product, and it's a very interesting product because it's always the same number no matter what you hook this op-amp into in terms of feedback. Okay? And that's what I want to show you in the rest of this lecture here. Right, so first of all, let's just start off with this. Let's look at a couple other things. If omega is much greater than omega b, just a little bit of shorthand here, then even in this equation you can neglect that 1. So this equation drops down to A naught divided by S over omega b. You get A naught times omega b over S, or omega t over S. Okay? So knowing the unity gain frequency of an op-amp pretty much tells you what its transfer function is for frequencies greater than omega b, greater than its 3 dB frequency. It's just omega t divided by S. It's like an integrator. So if I were working only at frequencies here on up, I don't have to express the op-amp transfer function like that. I just express it by this omega t over s. Looks like an integrator. Okay, so that's just some shorthand to know for all of this. But where am I going with all this? I'm showing you some properties of op-amps, non-ideal op-amps that have a finite gain, finite bandwidth. But what you're really interested in is how they perform in an actual circuit. Okay, so in an actual circuit, this is an actual circuit of an op-amp, right? It's going to have a certain frequency response. But what is the frequency response of this? So say this op-amp here is no longer an ideal op-amp. So in this case, we're looking at the case where this is not ideal. All right, it has finite gain and finite bandwidth. Okay, so let's analyze this. Let's find an expression for this circuit, which we have analyzed before, or at least you've analyzed before in EE40 and other courses, right? This is just a non-inverting amplifier. Okay, but let's now analyze it for the case where it has finite gain and finite bandwidth. Now, I think you've done this before, right? Is this true? Yeah, you've done it in 40. Okay, that's excellent, because that means even more cheating is possible. And there you go. Out of nowhere, right, we'll just do that analysis right here. So you know how to analyze this, right? You apply KCL at node 1, and I should at least write where node 1 is here. So that's node 1. If I apply KCL at node 1, right, I can no longer say that V plus equals V minus necessarily, right, because this has finite gain. So what I have to do is actually do the whole derivation for this, a brute force derivation where, I have this output voltage. So V out minus V minus is the voltage across R2. That's going to give me a current going there, which then goes into R1. So that then equals V minus over R1. I will still assume that the input impedance of this op-amp is infinite, which is a reasonable assumption if you have an MOS type op-amp, as you've seen. But I won't assume anything else, right? So I've written this equation. Then I can rearrange this equation to this and this. And finally, I end up with this equation here. V naught over Vi of S is 1 plus R2 over R1 divided by 1 plus 1 over A of S, where A of S is where I have plugged in this, right? I'm no longer saying that's infinity. I'm saying that's an A of S. And that A of S here is equal to that equation that I had before. It's A naught over 1 plus S. It's this. A naught over 1 plus S over omega B. So right here, that A of S is this. Okay? And so now what I want to do is plug in the value of A of S here. So I have this. And so here's where I'm not going to here I'm going to say A of S is this A naught over 1 plus S over omega B. I'm going to plug that into this equation, and I'm going to end up with V naught over Vi of S. Pull out this 1 plus R2 over R1. But then this whole second part of this, after you do a lot of math here, so I'm skipping the algebra here. So after the algebra, you end up with 1 plus R2 over R1 times 1 over 1 plus S over A naught times omega B times R1 over R1 plus R2. Okay? And that's great. That becomes the actual performance of this thing. Okay? So your gain still ends up being this 1 plus R2 over R1. Okay? Except, I am making some approximations in that too. So I'm saying the gain is large still. But I am saying that now your frequency response is now not going just to omega b. It goes to A naught times omega b times R1 over R1 plus R2. Okay? And this is actually a larger frequency than before. Okay, so when you put feedback around an op-amp, you actually end up with a larger frequency than before. And, you know, this is one way to look at it. So that's why I'm calling this the brute force derivation. There is another way to look at this feedback circuit that I think is very important for you to be able to do. So let's do this problem again, a second time. But let's now do it trying to look at it as an actual feedback circuit. Okay, so what do I mean by actual feedback circuit? Well, if I can find it, I can cheat some more there. And there you go, right? There's your actual feedback circuit, right? This is something we talked about before, right? It's basically this block here where I have this summer at the beginning. I have an error signal after the summer. I have this amplifier, A of S, just like the op-amp. And now I'm feeding that back through a beta here. Okay? And I was able to successfully steal that for some reason, though it ended up the wrong size. There it is. Okay. Okay, so what can I say about this? First of all, can I identify what the error signal and the beta signal are on the actual circuit here? Okay, because I can certainly see that I've got VI here. That's the same VI as that. This V naught is the same V naught as that. Where's my error signal? Well, then my error signal is just a signal across the plus and minus terminals of my op-amp. Okay? And my beta signal in this case is right there. And so you can see in all of these cases here, the error signal has to be equal to VI minus my beta signal, and you can see that's the case right here. Right? This total signal across here is VI. And VI is equal to the error plus the beta. So V error is equal to, I guess I'll write that here, VI has to be equal to the error plus the beta. And the error then conversely is VI minus the beta. So on my actual circuit, I have now identified something equivalent to this circuit here. Okay? And so what I want to do is determine things like what's beta. Because once I figure out what beta is, I can now plug everything into that feedback stuff that I did before. Remember the feedback stuff that I did before? If you don't, you will very quickly because I have, whoops, I guess I haven't cheated enough. I was going to cheat even on this second page, but I'm not going to. The last thing I do here, let me determine beta for you. Right? So if you look at this circuit here, actually let me do it this way. I get beta very quick, so don't worry. So if I look at this circuit right here, okay, I'm feeding back from V naught to beta, which is this voltage right here. So the real circuit that I have is V naught across this. This is R2, that's R1, and that's V of beta. It's a voltage divider, so I could just say that V of beta is equal to R1 over R1 plus R2 times V naught, or that beta, just rearranging this here, which is equal to V beta over V naught. That's R1 over R1 plus R2. So I now have beta. Okay? And if I have beta, I can now just write down the expression for the solution to this problem based on the system analyses I've done before. Okay? And I'm going to do that then in the next lecture, which will be on Friday, right now at 3 p.m. I'm going to see if I can move it to 2:30 p.m. If you came a little late, I passed out a sample exam and the midterm 1 information. So you might, I guess they're right up here in the front. You might come up and get those.